Hello once again, class, and welcome to another mock lecture. Today I just wanted to toss out a really short one about higher order derivatives. In the last video, what we talked about, we looked at this exact example. In the last video, we had g of x is equal to x cubed minus x plus 1. That's this red line that's graphed here. And then we calculated its derivative based on the limit definition of a derivative to be 3x squared minus 1. Right, and some of the stuff that we looked at was that the relationship that g has with its derivative is that when the original function, right, when g has a slope of 0, then the derivative was there was a 0, right? Since remember, the derivative is modeling the slope of the red line, the blue line models the slope of the red line, you'd imagine that where the red line has a slope of 0, an instantaneous rate of change is 0, that the blue line, the derivative, would have an x-intercept at that point. We also talked about things how on the intervals where your g function is decreasing, that has negative slope stuff, so you'd imagine that the graph of these slopes would be below the x-axis because it's negative. Okay, so these are all normal, quick review about relationships between a function and its derivative. But what if I told you that we could now find the derivative of the derivative? We could model the derivative's slope, right? We could look at the slopes of this line here. And to do that, it's really just doing the exact same thing that we did for the original function. We're just going to use the limit definition of a derivative to find the derivative of the derivative. And we're going to do the notation here as g double prime is typically how I say that. You could say the second derivative of g, but I always find myself saying g prime, g double prime, g triple prime instead of first, second, and third derivative. So when I'm referencing g double prime throughout the video, what I mean is the second derivative of the g function. And you'll notice that in the limit definition, I'm doing exactly the normal difference quotient stuff, except that I'm using g prime at every step instead of just g. So plugging it all in is relatively straightforward. I think at this point, we don't need to really go through too much stuff about how to actually find the derivative using the limit notation. And again, in this case, I mean the derivative of the derivative. It's a quadratic, so you just do normal quadratic stuff. Stuff cancels. You reduce by a factor of h, and so we end up getting 6x plus 3h, but when you're plugging in 0, now you can use direct substitution. So you just get that the second derivative of g, the derivative of the derivative, is just 6x. So I went ahead and graphed that line with the other two. This is now a family of derivatives, if you will. Notice that the blue line and the green line have very standard function with derivative function relationship stuff. For example, when the blue line has a slope of 0, the second derivative line has an x-intercept at 0. Where the blue line's increasing, the green line, the second derivative, is above the x-axis. So I think it's very clear to see that g double prime is very simply just the derivative of the derivative. And it actually does tell us some things about g of x as well, more of which we'll get into, I think, in a different video. You could go even a step further. You could find the triple derivative, right? You could find g triple prime, which again, using the limit definition of a derivative, now I'm using g double prime as the base, right, for this definition. This one is a linear function, so there's really not much work to do here, and you actually get that the triple derivative, right, g triple prime is just a constant function. It's g triple prime of x is equal to 6, which if I wanted to graph, I had to kind of extend my y-axis a little bit so that we could see it here. All right, so I think just from this, there's a decent amount of things that you could notice, right? We're eventually going to get to this point where finding derivatives can be simplified a little bit rather than having to go through this limit definition thing. And I think that this family of g functions here really showcases that kind of relationship for things that have specific powers, right? You'll notice that this was a cubic function. The next, the derivative of g was a quadratic. The derivative of g prime, or the second derivative of g, was a linear function. So g to the, it's x to the first. And then the third derivative of g was a 6x to the 0, which is just 1. So you just get 6. So there is a pattern happening there. And this is a relationship that we're going to talk about in a later video. But it is cool to see it here, you know, in action. Now, g triple prime being a constant function like this actually does make a lot of sense. If you look, because remember, it's modeling the slope of the function that came before it, of its antiderivative, as we'll soon learn that term to be. But this is just a y is equal to mx plus b sort of equation here, right? It's linear, and so it's no surprise that its slope never changes. It's always going to be 6. The slope of this line here is always going to be 6. It's got a constant slope, which is why the derivative of that function, the derivative of any linear function is always going to be whatever the slope of that line is. In this case, it happens to be 6. Okay, so the higher order derivatives, you have g of x, which is cubic, g prime, which is a quadratic, g double prime, which is linear, and then g triple prime, which is a constant function. And we can, of course, take more derivatives than this. In this example, the derivative, the fourth derivative of a constant, we'll find actually to be 0. So it's not very informative in this situation. So one common application of higher derivatives is motion. Maybe it's particle motion, maybe it's motion of a rocket, maybe it's motion of a car. It's just some physics application of motion. S of t is usually called your position function. The derivative of s of t is your velocity function, v of t. The derivative of the velocity function, or the second derivative of your position function, is your acceleration function. And then the derivative of the acceleration function, which would be the second derivative of velocity or the third derivative of position, that's your jerk function. And I've given it to us here in both Lagrange and Leibniz notation. Again, Leibniz notation going to be important to use later on. For now, it's just here's how you would write these higher order derivatives. Now, if you're wondering what do these mean, right, in kind of layman's terms, what is acceleration? What is jerk? What's the jerk function? I always fall back on thinking about them as just the rates of the previous function, right, before you took the derivative. Again, what we'll soon learn to be is the antiderivative. The position function is just a position function, right? It's modeling distance versus time. The velocity is the rate at which the position is changing. So it's the slope of the position function. Acceleration is the rate at which the velocity is changing over time. So it's the slope of the velocity function. The jerk function is the rate at which acceleration is changing over time. So it's the slope of the acceleration function. Jerk meaning in this case like sharp or sudden types of movements, things that are very erratic and change acceleration very suddenly, right? That would be a jerk. So let's look at one fun little example regarding some higher order derivatives, velocity, position, and acceleration. All right, so the three graphs below model a car's position, a car's velocity, and a car's acceleration. And all I want to do is I want to figure out which is which. Based on what we know about derivatives and the derivative of the derivative, what are some things that we can figure out about these three graphs here? Well, the first thing that I look at is as I say to myself, well, the function a, where its slope is 0, neither b nor c have an x-intercept, which means that b and c cannot be the derivatives of a itself, which automatically tells me a must be the acceleration. Jerk is not modeled here. There is no third derivative that's listed. We just have a position function. We have a velocity. That's just the first derivative of position. And then we have acceleration. The thing beyond that would be the jerk function. But in this case, it appears to be nothing is modeling the slope of a, which means that a must be acceleration, which I'm noticing I just spelled wrong. There's a missing e there. And that'll show up for the remainder of the slides, but that's okay. Pretend it's there. Use your imagination. The next thing I look at is, well, is there a function that models the slope of b? We already know a is modeling the slope of one of these two things. Is it b or is it c? Well, it looks like c never has a slope of 0, but b does. And it's exactly where a intersects the x-axis. So I'm pretty confident in saying at this point that b is going to be the velocity. Now, also something to keep in mind is that where b is decreasing, your acceleration function, which is the derivative of velocity, is also below the x-axis. So we don't have to just look at x-intercepts and see where that correlates with a slope of 0 for a different graph, although that is usually the first thing that I look at. But everything else, as far as relationships go for derivatives and base functions, still holds true here. This function is decreasing when a is below the x-axis, which means b has negative slope, and that corresponds to where a is below the x-axis, where the model of the b's slope is negative. Okay, so b is velocity, which means automatically that c is going to be position, which makes sense. There are actually a lot of things that we could say about the concavity, because like as it stands, the way that we figured this out was mostly by process of elimination, but we could actually use a to help us figure out that c is position once we start talking about things like concavity. But we're going to save that for another video. All right, so that's it. this is the one example that I wanted to do. Just wanted to hit you guys with a really short introduction on higher order derivatives and where they could be used and what they are. So hopefully you guys learned something. If you have any questions, please shoot me an email or leave a comment below. Thanks a ton for watching, and I'll see you in the next one.